In this video, we're going to continue the conversations of using integration to find the volumes of three-dimensional figures. One beautiful application of this method is that we can actually use this to derive the formulas for many of the three-dimensional shapes that we know the volume formulas for. In the first example that Julian showed you, he was talking about what we call a solid or a surface of revolution, where we take a two-dimensional graph and rotate it about something. But generally speaking, we don't need to be using specifically washers like that was created in that shape right there. If we have any three-dimensional shape and we superimpose it onto a two-dimensional graph, we actually can do this exact same process as long as we can calculate the area of these slices. So given some interval, we take some point within the interval and we take one slice. And in this case, again, I'm using this with respect to x. But we take a slice. This slice now will be an area. So the important thing is this, is as we slice up this object more and more, what we actually care about is the area of one of these slices. Yes, it has a volume because we have this delta x or this infinitesimal size when we integrate, but what we're focused on is the area. We create a formula for the area for any given x value, and then we iterate that using integration along the interval. So then, if we have a function that describes this cross-sectional area here, in this case we're talking in terms of x, and it's important we can do this easily in terms of y. You'll see an example of that very soon. But if we have a function that describes the cross-sectional area, knowing that we have this infinitesimal width that gives us actual volume, but that's not consequential at this point. If we can describe the cross-sectional area, then what we can do is integrate that cross-sectional area from A to B. This dx gives us that width of that cross-sectional area. If we integrate that cross-sectional area from A to B, then we do get the volume of that three-dimensional figure. This definition gives us a standardized process, which was supported by Julian's argument for using this figure, the solid of revolution that I described previously. We're going to do a bunch of these because they're very useful and important moving forward. Importantly, you'll see us using that disk method. I'll introduce the washer method here in a minute, but I wanted to make it clear that this method, and we'll see examples of this, does not have to be this circular or this rotation around an axis. We could do this as described here with any figure as long as we have a formula in terms of the variable with which we're iterating that can describe the cross-sectional area of these pieces. All right, in this example here, what we're going to do is find the volume of the solid that's obtained by rotating the region that's bound by y equals 1 over x squared, y equals 1, and y equals 4. So to attack this problem, what I've done here is sketch just the positive side of y equals 1 over x squared. Importantly here, just to note, just to say when you're dealing with this does have is two-sided here. This comes from exactly the same shape on both sides here. But since I'm going to rotate this around the y-axis, there's no reason for me to consider this part right here. What I'm going to do is think about this length right here and rotating that around. So generally speaking, what's going to happen is I'm going to take this, I'm going to rotate this around right here, and it will create this shape right here. Importantly in this case, what we have are these cross sections that are again disks, just like Julian's example. But in this case, we have disks that are laying flat horizontal here. In this case, the thickness of these washers is not a change in x. We would think of this as a change in y. And this is important now. So what we're going to do with each of these washers, again, the volume is made by this width. We're thinking about the area using that previous discussion right there, but we're going to be doing everything in terms of y because that's the thickness of our cross sections. And again, for the area, we're simply using the area of a circle pi r squared. The important thing is this r right here, how we describe this radius. So to describe our radius, what we know about the relationship here is that y equals 1 over x squared. And again, we're talking about this in terms of y because we're going to iterate these cross sections from 1 to 4 on the y-axis. And this radius right here is actually an x value. So if we just take this relationship right here and solve this thing for x, we'll get 1 over y, take this square root, we get x equals 1 over the square root of y. We actually get that plus minus, but there's two reasons that's not important. For us, in this case, we're considering these x values in this first quadrant right here as our radius. And we could do the same thing over here on the negative side, but importantly here in this case, since we have this r squared, it wouldn't matter which one we use. But anyways, this right here, x equals 1 over the square root of y, describes this length because this curve is described by this relationship right here. So then our cross-sectional areas are described, in this case, in terms of y, as pi r squared, which is 1 over the square root of y squared. And so our area, in terms of y, would simply be, let's write it as pi over y. So that really is the majority of the work. Again, what we've done is describe these cross-sectional areas in terms of y, motivated by the fact that our cross sections had a thickness of y. And so now we can use that formula we were just talking about to get the volume of this shape is going to be the integral from 1 to 4 along the y-axis of pi over y dy. Again, that dy is this infinitesimal width that comes from that delta y. All right, then to evaluate this integral, we have pi over y, which we can pull the pi out, and it's just a 1 over y. We know the integral of that is the natural log of the absolute value of y, and we're evaluating this from 1 to 4. Then just finishing this evaluation, all we need to do is plug the 4 and the 1 in and subtract the values to evaluate it. And what we get in this case is the natural log of 4 minus the natural log of 1. We know the natural log of 1 is just 0, so this is doing nothing. So we get the area of this solid revolution is pi times the natural log of 4. So these objects that we've talked about in these first two examples are called solids of revolution or surfaces of revolution. And what we've shown you is what we call the disk method, where if you rotate this around the axis, and just to note here, you're probably getting it, if you take this region and you wrap it around the y-axis or any vertical axis of rotation, you're going to have these disks that have a width of y, and you're going to integrate with respect to y. If you wrap them around a horizontal axis like the x-axis, your washers then are going to have a width of x, and you're going to integrate with respect to x. In the next example, we're going to do exactly the same treatment. The big difference is these cross-sectional pieces that we're going to look at aren't going to be these nice discs that are completely filled in. Instead, they're going to be washers. But the beautiful part is the general technique is going to be exactly the same. All right, in this example right here, what we're doing is taking the region bound by y equals 1/4 x squared, y equals 0, and x equals 2, and we're rotating it about the y-axis. So here is the region described that we're rotating, and we're rotating this around. And so what we'll have is this shape that looks something like this. So these pieces will look like this and come around. Importantly though, as we go around, the whole middle is not filled. This is open when we rotate this around. So what we'll actually have is this washer shape where we'll have area on these cross-sectional pieces around here, but we'll have a gap in the middle. So hopefully you can get an idea of what this figure looks like and what these cross sections look like. This object actually, it looks like one of those steel drums, you know, from like the Caribbean kind of music sound with the steel drums where they drum on the inside. I would try to make the sound, but it would sound absolutely ridiculous. But to move on to the idea of finding this area, importantly, these cross-sectional pieces have these gaps in the middle. So they're not actually these discs that we've done before. Here, what I'm going to do is rotate one of these. Actually, before I talk about that, I want to say, and this connects to what I said before, but the width of each of these cross-sectional pieces will be a delta y. So we have these areas that we're going to be focused on when we do our integration, but we always want to know where's the width of each of these cross-sectional pieces. In this case, that height or the width of the cross-sectional pieces is in terms of y, which is a lot of things for us, but most importantly, as we do all our calculations, we want to make sure we put our information in terms of y. So let's describe this. So this object right here, what we're going to do, this is a composite circular figure. I'm sure you've seen stuff before. Just in context, when you look at this, what you do is you think about the area of the whole figure and you think about punching out the area in the middle. So the first thing is to figure out is what is the radius of this circular object from the middle here to the outside. Well, the outside of this actually stays constant. So if you think about here, we're in the middle of this figure, this cross-sectional piece. We go all the way to the outside right here. We have this boundary of x equals 2 that actually does not change. So this radius right here, the outer radius is always 2. The inner radius in this case, this little circle we're going to subtract out does vary, and that's what creates this shape right here. The inner radius is described by the x value of this quadratic right here. So as we go down, or if we can think about from going from bottom to top, the outer radius is always 2, but the inner radius of the cross-sectional piece will change. As we go from here, there's almost no inner radius, and then we get a bigger inner radius until we meet up at this point right here. So this inner radius is described by this x value. That x value is determined by this relationship between x and y. And so what we'll do right here is take y equals 1/4 x squared. And we're going to solve this for x. So we get 4y equals x squared. Square rooting both sides to get 2 square root y equals x. So then the area of this cross section is determined by this outer radius right here. So we have this outer circle, and we'll compute that whole thing. That's pi r squared. So 2 is 2 squared. Well, it's just 4. I'll write 2 squared right there. And we're going to subtract out or punch out this inner circle here, which is pi times the radius. Now this radius changes for my x values. My radius in terms of x right here, in terms of y, excuse me, is 2 square root of y squared. So that gives us the area of these cross sections in terms of y is 4 pi minus 4 pi times y. And just to emphasize this, because this is an important technique, these washers, not just the disc, but these washers that have these holes punched out, when you do this, it's the same every time as the good news. You have the outer radius, or in this case, we'll call this the outer circle, because we've calculated all of that. We put the radius in here, and this is the inner circle. As with the last example, that's most of the fun. The only thing I don't have down right here is I know I'm going from y equals 0. So I want to integrate on the range from y equals 0. And then I want to go to the top of this right here. I need to figure out where these two meet. Specifically, if I find this point where they intersect, then I'll know the y bound right there. And so all I need to do in that case, I could just kind of throw numbers in and figure it out. What I'm going to do is figure out what y equals when the x equals 2. So just real fast to show that. So I got 2, y equals 1/4 times 4, which means y equals 1. And so what we're going to do is integrate from y equals 0 to y equals 1. So there we have all the pieces. Our volume then is integrating for y from 0 to 1. Our cross-sectional areas are described by this right here. So we have 4 pi minus 4 pi y, and then dy. And again, that dy is with respect to y is our area, but also because these cross-sectional pieces have these little widths of y. So continuing to integrate this, pretty straightforward. 4 pi would be 4 pi y. Here we're going to use the anti-power rule. Y squared divided by 2 I'll just divide this by 2 to get 2 pi y squared, evaluating from 0 to 1. And beautifully, since we have 0 is pretty inconsequential because both these terms have y, we'll just be subtracting away nothing. I plug in a 1 here, I get 4 pi minus 2 pi, which simplifies down to 2 pi for the area of this solid of revolution. So just before we're done in this video, all I'm going to do is just generalize these two processes we talked about that are really important. Is the disk method, so where you just have this disk, the cross-sectional section is this disk created by the solid of revolution. In this case right here, we instead call this the washer method because we have these outer circles and these inner circles that we need to subtract out for each of these cross-sectional pieces. So generally speaking, for these objects that we call the solids of revolution, we know we can produce the volume with integrating the cross-sectional area. AX is the cross-sectional area from A to B. I'm just using X in this case. Obviously, I've shown examples in this video of using Y. So use any variables. Could even be something like theta or something else like that. But we have these two methods we've talked about just to review. We have the disk method. And in this case, A of X equals pi times the radius. Almost always, if it's interesting, described by some function, has to be in terms of X or in terms of whatever variable we want to integrate with. And again, that's determined by where's the thickness of these cross-sectional pieces, that radius squared. And if we use the washer method, in this case, we have these gaps that we need to take care of. We need to punch out this inner circle, and it's always of the same form. Our cross-sectional area in that case will be pi times the outer radius. That gives us the area of the big circle if there was no hole in it, and then we need to take away that inner circle, and we take pi times the inner radius squared. We give a bit extra focus. Last thought is that we give a bit extra focus to these solids of revolution because they do come up often in context. And also, they can be used to prove that the formulas of many of our geometric shapes that have any kind of circular part, like cylinders, spheres, and other objects. And just to say, and I won't show an example of this, but I think it's a fun experiment for you to think about, is you could prove the formula for the volume of sphere given everything that you know so far. So for instance, if you knew the equation for a hemisphere that has a radius of r right here, so we go from r here and we have negative r right here. So if you knew the definition, the formula for this object right here, which you do, by the way, it's just y equals the square root of r squared minus x squared. And then if you took that and you rotated it around the x-axis, you could derive the formula for the volume of a sphere.